I'm Lee Felsenstein. I was instrumental in the early personal computer industry. I saw how it grew beyond all expectations in a process involving thousands of people. I'd like to do this again, this time building an industry segment that enables kids to reach their best potential with the technology. Recently, I found that basic bit-level programming operations are being removed from the computer science curriculum in favor of high-level languages. Bit operations never did require a college education to understand. I learned the basics by the time I was 12. Without a firm understanding of these bit operations, teaching high-level languages isn't computer science at all. It's teaching magic. So I'm starting a branch of STEM education that lets middle school-aged kids learn these bit operations as a stepping stone to learning real programming. There's a form of code that operates at the lowest level. The term for this is microprogramming. With microprogramming, you can build small programmed machines. More formally, these are called state machines, invented by Alan Turing in the 1930s. The state machine is the tiniest, simplest example of a computing device, combining its own outputs with external inputs according to rules set by the user. I've designed and prototyped a product called AndOrBit that lets users set these rules not by typing symbols on a keyboard, but by inserting pegs into holes and observing lights as you push a button to move from one state to the next. The pegs are tiny diodes, inexpensive electronic components that you handle with tweezers. The logic equations or expressions that you write tell you into which holes to insert them. If you're right, the behavior follows the rules you've written down. If not, you just dump the pegs and start again. What you learn along the way is how to write down the intended behavior of the device, how to compose this behavior out of a number of simple elements, how to define each element's behavior through simple expressions using the basic Boolean operators and, or, and not, how such expressions can be understood as simple patterns learned in a visual tactile process rather than abstractions, and how computers work as pattern-generating machines controlled by the same kinds of patterns they generate. As an outcome of this learning process, you gain a conceptual basis for learning computer programming by understanding the fundamental physical and logical processes at work under program control. Maybe this sounds interesting on an abstract basis, but in fact it is much more concrete. While the device initially uses switches and lights as inputs and outputs, it also has input and output connections that can sense and drive real things. Think lights, buzzers, and motors for outputs, and coin boxes, light sensors, and motion sensors for inputs, among others. Several AndOrBits can be interconnected to make bigger systems, enabling students to work together on group projects. It will even be possible for a larger class with good instruction to build a working replica of a PDP-8 mini computer, for which software exists. Of course, this lone student can't get too far without assistance and mentoring. When I was learning, I avoided letting anybody see that I didn't know it all. This slowed me down a lot. I therefore decided to build in a means of allowing others to assist the learner through an external connection to the Internet. Mentors on the Internet will be able to examine the pegboard setup, drive the inputs, outputs, and clock, read the outputs, and give advice. This will require software and web services, but the basic hardware channel will be there. I hope that AndOrBit will stimulate the development of a new segment of the STEM field, one with both this device, a range of peripherals, courseware for the students, and software and web services to support mentoring. An ecosystem like this would enable kids to experience how software emerges from hardware. Armed with this understanding, students will be prepared to learn all sorts of programming. Some will follow the path of the hardware, and some will simply use the skills gained to build logic machines that do their bidding. I want to involve early adopters who can create the courseware, system designs, and supporting structures for this bit-level programming. I'm also addressing people who want to participate in developing a new industry segment, one that allows young people to gain a strong grasp of how computers compute. Let's make this a reality. The engineering work for the basic device is already done, and using a prototype, I've worked with kids to discover how they can learn. Please look further to find out how you can participate. Thank you.